In this lecture, we are going to discuss the topic of potential energy as an equilibrium criteria. So as far as our syllabus is concerned, this is the last topic of our course, engineering mechanics. So if we focus our attention on this topic, potential energy as an equilibrium criteria, in addition to the equilibrium criteria we discussed in the first unit, where we considered a rigid body, and if some forces and the couples were acting on that rigid body, then the resultant force and the net moment on that rigid body should be zero for the body to be in equilibrium. One more criteria we had discussed just a few days back, that is the virtual work criteria. How we use the virtual work criteria for the equilibrium of a rigid body or equilibrium of a system of connected bodies. Now this potential energy criteria is also a part, or we can say that it is an extension or a subset, in fact, of the virtual work criteria, where we consider the virtual works only due to the conservative forces. And the work done by those conservative forces are to be represented in terms of the changes in the potential energy. So first of all, we have to learn about the conservative forces. And for that, we have taken an example of the conservative force, that is weight. Weight is a conservative force. Okay, let's see what is the work done by a weight. In the schematic, you can see here, it is taken from the Beer-Johnston text. There is a block A. Okay, it has an initial position of A1, and along this path shown by the blue color, it is attaining a final position of A2. The position A1 is at a vertical height of y1 from the ground, and the position y2 or A2 is at a distance of, or at a height of, y2 from the ground. Now let us consider an intermediate position A of the block. Okay, this is the block at some intermediate position, and that intermediate position is at a height of y from the datum or the ground. Let's say that this block gets displaced from position A to A dash. Let's treat this position to be A dash. And during this displacement of this block from A to A dash, the vertical displacement of the center of gravity, we can see that it is equal to dy. That is, the center of gravity is being displaced vertically upwards. And we can also see that this is the weight force. Okay, this is the weight force which is acting in the vertically downward direction. Now weight force is in the vertically downward direction, and the displacement of the center of gravity is in the vertically upward direction. We can say that during this instant, the work done by the weight will be equal to du, that will be given by the product of the force and the displacement. Now, since the force is acting downwards and the displacement is upwards, therefore, this work done will be negative, and it will be represented by the force, that is the weight in this case, multiplied by the distance traveled by the center of gravity, which in fact is equal to dy. So this du is equal to minus dy. It represents the small work done by the weight force when the body gets displaced from its position A to A dash. And see here, these are the actual displacements. Therefore, dy is not written as delta y, neither del u is written as, neither this work is represented by del u. Okay, it is represented by du, because these are the actual works and the actual displacements. Now, what will be the total work done when the block is displaced from A1 to A2? Okay, work done by the weight when the block gets displaced from its initial position A1 to the final position A2. Then we can say that the work done when the block is displaced from initial position 1 to 2, that will be given by the integral of this above equation. That is equal to minus w dy, where weight is constant, therefore dy is the variable, and the block changes its position from the height y1 to the height y2, okay, attaining the final height equal to y2. Now we can solve this. It will be minus w y2 minus y1, or we can say that u1 to 2 is equal to now this equation represents the work done by the weight when the block is displaced from the initial position 1 to the final position 2. So from here we can note that this work done is equal to change in some function. Okay, this work done is equal to change in some function. is equal to a change in function, and that function is equal to wy. Okay, we can see that there is an initial value of wy, that is wy1, and there is a final value of the function wy, that is wy2. Okay, so we can see that this work done is actually the function of wy, which in fact w is a constant, therefore it is actually the function of y. That is, this work done is the function of position. So it does not depend upon the path. Let me take another path. If I consider this to be the another path from position A1 to A2, if I move the block along this path, then the work done still would have been wy1 minus wy2. If I had considered this path here and the block was moved along this path from position 1 to 2, the work done would still have been wy1 minus wy2. Therefore, we can say that the work done is a function of, okay, it is a function of some function, okay, which is the function here is wy. Okay, the function is wy. Work done has been represented in the terms of the change in function dy. Okay, you can see that wy1 minus wy2. Okay, so this is the function, okay, whose change is equal to the work done here in this case. Okay, fine. Now what we have seen from this case is that if u1 to 2 is equal to and we have seen that u1 to 2 is a function of y. Okay, therefore we can say that from here we can see that work done is independent of, rather work done by the weight is independent of the actual path followed. Okay, it depends on initial and final configuration of the system. Okay, therefore work done is a conservative force, work done by weight. Work done by the weight is a conservative force. What does that mean? It means that if there is a force, okay, and it does work, and if that work depends only upon the initial and the final positions, okay, then the work done by that force will be depending upon the initial and final position, and then we say that this force is a conservative force. Okay, now from here we can see that from this equation, okay, let's write this equation again. u1 2 is equal to wy1 minus wy2. So work is given by change in a function wy. Therefore this wy is a potential function. And in this case, since this is a work done by the weight, this function, okay, the work done by the weight is represented in change of this function. Therefore, this function is termed as gravitational potential energy. okay, and it is represented by Vg. So Vg is equal to Wy. Okay, it will have different values when measured at different heights from the datum. Okay, y1, y2, y3. Okay, these are the heights which are measured from the datum. Therefore, the gravitational potential energy of a system will be the function of the height, and it is represented by Vg. So if I modify this equation, we can say that u1 to 2, that is the work done in moving the system from position 1 to 2, is equal to the change in the gravitational potential energy. So this is equal to the difference of initial gravitational potential minus the final gravitational potential energy. Okay, it is the change of this potential function. Okay, so we can say that this work done is represented by the change in gravitational potential energy. To be precise, we can say that work done by weight is represented by the change in the gravitational potential energy. Okay, so in this equation we can see that from this equation we can see that in our case, okay, Vg1 is less than Vg2. Okay, you can clearly see from the schematic the potential energy of this block, gravitational potential energy of this block at this initial position will be equal to Wy1. Okay, and the gravitational potential energy at this final position A2, that will be equal to Wy2, and clearly y1 is less than y2. Therefore, the gravitational potential energy of this block at this initial position will be less than that of A2. Therefore, we can conclude here is that Vg1 is less than Vg2. Therefore, work done will be negative. Work done is negative. Therefore, the work done by the weight is negative. Obviously, the work was done against the displacement. Weight was acting downwards and the displacement is upwards. Therefore, this work is negative, which means that the initial gravitational potential energy is less than the gravitational potential energy at the final position, which is at a greater height. Okay. Therefore, we can conclude that work done is negative, which means potential energy is increasing. In fact, gravitational potential energy is increasing. Okay, so now let's consider another case. If y1 would have been greater than y2, then we can see that Vg1 would have been greater than Vg2. Okay, Vg1 would have been greater than Vg2. Therefore, work done would have been positive. Work done would be positive. And we can see that in this case, gravitational potential energy is decreasing. Gravitational potential energy is decreasing. So what we have seen in the first case, which was our actual case, if work done is negative, gravitational potential energy is increasing. If work done is positive, then the gravitational potential energy is decreasing. So we can just make a statement or make a conclusion here is that du is equal to minus change in the potential energy, where dv is v2 minus v1. Okay, the change is means final minus initial. Okay, again from this equation we can see that in the first case work done is negative. So if this work done is negative, then gravitational potential energy is increasing. Therefore, if one quantity is decreasing, another is increasing. Similarly here, work done is positive, gravitational potential energy is decreasing. Therefore, the relation between them is what? The relation between them is du is equal to minus dy, because if one quantity increases, another quantity will decrease, or if one quantity decreases, another quantity will increase. So this is the relation which we can infer from the above discussion. Okay. So what we have seen here up to this point is that weight is a work done by the weight is depending upon only the initial and the final position of the system, not upon the intermediate path followed by the system in achieving that final state. Therefore, the work done by this weight is equal to the work done by the weight is independent of the path followed. Hence, we can say that the weight force is a conservative force. So this is the first example of a conservative force. Okay. Now let's see another example of a conservative force, which is the spring force. For that, we have to look at a schematic again. And this again has been taken from Beer-Johnston. So see here, this is the initial position of a spring. Okay, one end of the spring is connected to the fixed part and another end is connected to a block which is free to move in the along the horizontal direction. Okay, so we can see that this is the undeformed position of the spring, and this distance is usually taken as L naught. Okay, it represents the undeformed position of the spring. Now if now this is an extended position of the spring. Okay, you can see that the second figure represents the extended position of the spring. The spring is being extended by a distance of x1. This is the extension in the spring. Okay, so what would have been the small force if we take an intermediate position? Okay, if we take any intermediate position, the work done by the spring force would be equal to spring force multiplied by the small displacement. Okay, what we have considered here is, if we consider a small displacement, suppose this is one position of the block at a distance of x, and we can see that if this block is getting displaced by a small displacement dx, then the spring force would have been in the opposite direction, and that is the restoring force. So work done by this restoring force would be equal to, the work done by this restoring force will be equal to the restoring force multiplied by the small displacement dx. Okay, here we are assuming that the block is being getting displaced by the small displacement dx. Okay, now we can also see that the restoring force is in one direction, and the spring force, the restoring force is in the towards the negative x-axis, and the displacement is towards the positive x-axis. Okay, therefore this work done will be negative because the restoring force and the displacement are in opposite directions. So what would have been the total work done in displacing the spring from its undeformed position to an extension, what we call as the x1? Okay, the work done that would have been done by the spring force, work done by the spring force from displacing the spring from an undeformed position to an extension of x1, that will be equal to minus integral of, we can see that the spring force is represented by kx. Okay, the intermediate position which I took, the spring was at an extension of x. Okay, in this case the spring was an extension of x, therefore the spring force would have been, it would have been equal to kx. Okay, and the displacement is dx. So this is integral of x dx and the displacement of the spring, the extension is from, initially it was undeformed, and let us say that it assumes a final extension of x1. So this will be equal to minus k x1 square by 2. Okay, so we conclude that the work done by the spring force in displacing the spring from an undeformed position to a position where its extension is equal to x1, that is equal to minus 1 by 2 k x1 square. Okay, now had the spring been initially at some extension x1, okay, now what we considered here in the first case is that the spring is undeformed and we extend it to an extension of x1. Now let's say that we further extend it from a to a1, a1 to a2. Okay, now in the first case this a0 was the initial position and a1 was the final position. Now let's consider the second case where the spring is originally extended. Okay, case second, spring is originally in extended position. Having an extension of having an initial extension, in fact, x1. Okay, so the spring is already extended by a distance of x1. Now from this extended position, from this originally extended position, we are further extending this spring so that it attains a final state represented by a2. And the total extension of the position a2 from the undeformed position is equal to x2. So what is the work done while we extend it from an initially extended position a1 to an another extended position a2? Okay, so that will be given by us the difference. Okay, that will be given by the difference of extending the position, extending the spring from an undeformed position to x2, x1, and extending the spring from undeformed position to a2. Okay, now let's see. Taking the schematic again, we can see that work done by spring force when spring extends from initial extended position to another extended position. Okay, so we see what is the extension, we see what is the work done by the spring, or we can write that work done by the spring force from an initial undeformed position to an extension of x1, that is, we have already seen it is equal to minus 1 by 2 k x1 square. Now let's see what is the work done by the spring force from an undeformed position to a final position of a2 where the extension is equal to x2, that will be equal to minus 1 by 2 k x2 square. Therefore, work done in extending the spring from initial position of extended position a1 to an extended position a2, that will be given by the difference of these two. Okay, that will be given by the difference of these two, that will be equal to u02 minus u021. That is, it is the difference of the work done by the spring force when the spring gets extended from the undeformed position to the final position, minus when the work minus the work done by the spring force when it gets deformed from an undeformed position to a position of uh, extension x1. Okay, so this will be equal to minus 1 by 2 kx2 square minus 1 by 2 kx1 square, and it can be seen that it will be equal to 1 by 2 kx1 square minus 1 by 2 kx2 square. So let's write this equation again. U12, that is work done by the spring. Work done by the spring force, that is equal to 1 by 2 kx1 square minus 1 by 2 kx2 square. Okay, note that x1 is less than x2. Therefore, u1 to 2 is negative. Work done by the spring force is always negative because the work done by the spring force is always against the displacement. Okay, it's quite obvious that this work done by the spring force will be negative. Okay, now again see that this equation can be written as the difference of a function. Okay, it can be represented by the difference of initial value of a function and the final value of a function. Just like in the previous case, weight, the work done by the weight was represented by the initial value of the gravitational potential energy minus the final value of the gravitational potential energy. Similarly, here in this case, this is again, that is the work done by the spring. Okay, we can write this as work done by spring is obtained by the difference of initial and final values of 1 by 2 kx square. There in the previous case the function was wy. Here the function is 1 by 2 kx square. Okay, again we can see that the work done by spring force depends on initial and final position. Okay, it depends upon the initial extension and the final extension. Therefore, the work done by the spring force depends on the initial and the final positions. Again, from here we can conclude that the work done by spring force is independent of the path followed. When work done by any force is independent of the path followed, then that force, which means that spring force is a conservative force. The spring force is a conservative force. And we have seen that in the previous case as well, the work done by a conservative force is represented by a change in some potential function. Okay, we can see that we have already seen in the previous case, work done by a conservative force is equal to a change in potential function. In the previous case, the potential function was Wy, and that was known as the gravitational potential energy. Here in this case of the spring, the potential function is 1 by 2 kx square, and that will be known as the elastic potential energy. Therefore, I can again write this equation u1 to 2, that is equal to 1 by 2 kx1 square minus 1 by 2 kx2 square. Therefore, in general, 1 by 2 kx square is a potential function, and this potential function has been given the name of elastic potential energy. Okay, it has been given the name of the elastic potential energy. So we can see that we can also write it, and this elastic potential energy will be represented by VE. Therefore, I can write that U1 to 2 is equal to the initial value of the elastic potential energy minus the final value of the elastic potential energy. Okay, so we can again see that in this case, okay, if you just see this equation, we can see that x1, in my case VE1, is less than VE2. Okay, isn't it? VE1 is less than VE2 because x1 is less than x2. You can see the schematic again. This x1 is less than x2, therefore we can see that VE1, okay, the potential function is 1 by 2 kx square, therefore it is dependent upon the value of x, directly proportional to x. We can see that since x1 is less than x2, therefore VE1, that is the elastic potential energy at the initial state, will be less than the elastic potential energy at the final state. Okay, so therefore we can see that since it is less, work done is negative. And also from the same equation, you can see that here the elastic potential energy is less, and here the elastic potential energy is greater. Therefore, work done is negative and potential energy is increasing. So again, we can see that du is equal to the negative change in the potential energy. Du is equal to the negative change in the potential energy, just like we had seen in the previous case of the gravitational potential energy. Okay, again the work done is negative, the potential energy is increasing. Okay, so this is all regarding the conservative forces, and let's see now how to apply these conservative forces to obtain the condition of the equilibrium. Okay, fine. Now let's make the conclusion of the discussion which we have been doing so far, and put it forward in the form of a statement written here. Work of a conservative force is independent of the path followed and is equal to minus the change in the potential energy. Okay, so we have seen this result that the work done by the conservative force is equal to minus times or the negative of the change in potential energy. Thus we say that if a force satisfies this equation, if a force satisfies this equation, the force is said to be a conservative force. Okay, and one thing to note here is in this equation, the work done is du is an exact differential. Okay, the work done du is an exact differential. So what do we mean by exact differential? So you might have read in the thermodynamics in the 11th class, if this is the pressure volume diagram of a gas, okay, of an ideal gas, let's suppose, if this is the state 1 of a gas, and let's suppose that this is the state 2 of the gas, okay, this is the initial state, this is the final state. Now, while moving from 1 to 2, okay, if we are moving from the initial state to the final state, we can move through different paths. Let's say that this is the path 1, okay, if this is a process 1, this process 1 is following this path. Okay, let's take this to be path A. Another process, okay, we are reaching the same initial and the final states. That is, we are having the same initial and the final states. This could be another path. Let's say that this is path B, and let's say that this is path C. Okay, see, the initial and the final states are same, but we know that the work done, okay, the work done is equal to PdV, or we can say that we always write a cut here, okay, dW, but we make a cut on this D to say that it is an inexact differential. Because work done in this thermodynamic process depends upon the path followed. Okay, so the total work is obtained by integral of PdV, that is the pressure volume diagram, area under the pressure volume diagram. So path for the path A, okay, work done is the largest. Okay, if you just uh, draw the projections of these 2 points, and the area under the path will be maximum. Therefore, work done when an object moves from the initial state to the final state along the path A is greater than the work done when an ideal gas, okay, or a system moves from initial state of 1 to the final state of 2 along the path B, and that in turn will be greater than C, because the area under this PV curve will be least for the process C. So initial and the final states are same, but the processes are different because they are following the different paths. Therefore, here in this case, the work done is an inexact differential. It is not an exact differential. We can't represent this work done in terms of the change in some properties. Okay, so if you remember the thermodynamic quantities, we say that dV is equal to, that is volume, V2 minus V1. This is a change in volume. Here there would have been V1. Okay, this is the volume axis. Don't confuse it with this potential energy. This is volume 2. Change in volume is equal to V2 minus V1, irrespective of the path followed. The change in volume is equal to V2 minus V1. Therefore, this is an exact differential. Similarly, if this is P2 and if this is P1, then we can say that the change in pressure is equal to P2 minus P1. Again, it is an exact differential. Okay. Similarly, temperature, okay, T2 minus T1. The change in temperature can be represented by T2 minus T1. But we can't say that work is equal to W2 minus W1, because there is nothing like work at 2 minus work at 1, because it is a path function. It depends upon the path followed. Similarly, if you can remember the heat transfer, okay, heat transfer during a process, suppose process 1 to 2, the heat transfer is given by the area under the temperature entropy curve. Okay, and this dq is equal to TdS. Again, this heat transfer is an inexact differential. Is an inexact differential because the heat transfer will be different for different paths. For this path A, the heat transfer, okay, we can see that this dq will be, or the net heat transfer, that will be equal to integral of TdS. That will be given by the area under this temperature entropy plot. Okay, it will be having one value For this path, if there is another path, let's say that this is path B, this area will get reduced. Okay, we can say that the heat transfer for the path A is greater than the heat transfer for the path B. Okay, although the initial and the final states are same, but heat transfers are different, because heat transfer, just like the work transfer in the case of the thermodynamics, depends upon the path followed. Therefore, heat transfer and the work transfer in the case of thermodynamics, we can't represent them in the change of some property. Okay, so but work done by a conservative force can be represented by the change in a property, and that property here is the potential energy. Thus, whenever any quantity can be represented in terms of the change in the property, we say that that quantity is a exact differential. Okay, work done by conservative force will be considered as an exact differential. Okay, so we can also say that, so finally what we have concluded here is du is equal to minus times dv, that is the work done by a conservative force is equal to minus times the change in the potential energy, and this can also be written as u1 to 2, it will be equal to minus times v2 minus v1, or this can also be written as u1 to 2 is equal to v1 minus v2. Okay, so we can remember both these statements. So now let's come back to our original problem of the virtual work. Now, virtual work for conservative forces. Okay, in fact, I can write it as an energy equation here. I can rename this topic to be energy equation. Okay, so from the principle of virtual work, what we know is the virtual works by all the active forces is equal to 0. That is, their algebraic sum is equal to 0 for the equilibrium. Okay, now consider a system when we apply virtual work equation. Okay, when we apply virtual work equation to a system with springs, and change in vertical position of its members, we may replace the work of the springs, work of the spring forces, in fact, and work done by the weight. By the negative, okay, Fine, by the negative of the respective potential energy changes. So what was the virtual work? The virtual work principle is that summation of, or rather algebraic summation of all the virtual works done by all the active forces is equal to 0. Now this virtual work term may contain, you can see that this virtual work term may contain some terms which are non-potential. The it may be it may contain the non-potential forces or the forces which are non-conservative. You can see that it can be divided into the virtual work done by the non-conservative forces and the virtual work done by the conservative forces. Okay, so we can see that this delta u dash is virtual work done, virtual work of non-conservative forces. And this delta uc is the virtual work of the conservative forces. Okay, so we can see that this has to be 0 from the virtual work principle. We can see that this delta u, the total virtual work, is the summation of virtual work of the non-conservative forces plus the virtual work of the conservative forces. Now the virtual works, due to the conservative forces can be the virtual work due to the gravitational forces, or we can say that the virtual work due to the weight plus the virtual work due to the elastic forces, that is the virtual work of the spring force. Now what does this statement say? When we apply the virtual work equation to a system with springs and the change in the vertical position, that is when the spring forces are considered and the weight forces are considered, that is the change in the vertical position. Whenever there is a change in the vertical position, we say that the work is done by the weight. We may replace the work of the spring forces and the work done by the weight by the respective changes in their potential energies, because we know that the work done by a conservative force can be represented by the change in the potential energy, and that to the negative change. We can again use this statement here. Work done by a spring force. Here it was actual work done, but in our case now we are focusing on the virtual work. Therefore, we can replace that this du by delta u, and this dv by delta v. But the statement will be same, that is the work done by a conservative force can be represented in terms of the change of its potential energy. Now coming back here, we can write delta u is equal to delta u dash. This is the virtual work due to the non-conservative forces or the non-potential forces, plus this can be written as minus delta vg, and this can also be written as the change in potential energy due to the elastic forces. Work done by the this virtual work done by the elastic force is equal to the change in the negative change in the potential energy, or a negative change in the elastic potential energy. Similarly, this change this virtual work done by the weight, or the gravity forces, is equal to the change in the negative it is equal to the negative change in the gravitational potential energy. So this is the mathematical statement of this statement written above. Now further, what can we say here is, I can further modify this statement. Delta u can be written as delta u dash, taking this minus out of this brackets, we will have delta vg plus delta ve, or we can say that this has to be 0. Now we can say that delta u dash minus delta V, okay, it is equal to 0, where delta V is equal to the total change in potential energy, okay, it is the total change in potential energy. And it is equal to the summation of the change in the gravitational potential energy and the change in the elastic potential energy, okay. So in this equation here, we have just broken the virtual work energy term in two terms, okay. One is the virtual work done due to the non-conservative forces represented by delta U dash, and other is the virtual work done and due to the conservative forces, which we have represented in terms of the change in the potential energy due to these conservative forces, okay. So finally, what can we conclude here is delta U dash is equal to delta V, okay. Now this system here includes this system, okay, this equation is for the system where which the active forces are, okay, the active forces. I have discussed that active forces are those forces which are responsible for the virtual work, okay. Active forces can be represented in terms of the virtual displacements. Therefore we can say that active forces are the forces which are responsible for the virtual work. Now this equation here, okay, this equation here, this includes both the active forces which are either conservative or non-conservative, okay, because this term is for the virtual work due to the non-conservative forces and this term is for the virtual work due to the conservative forces. Now if we have a system where the active forces are only the conservative forces, okay, considering a system where we have active forces to be only the conservative forces, then the virtual work done, total virtual work done will be only due to the conservative forces, okay. So when we have only conservative forces as the active forces, then the non-conservative forces won't contribute to the virtual work, and the total virtual work will be due to only these conservative forces. And for that, the net virtual work can be represented of the whole system can be represented in terms of the changes in the potential energies, okay. So what I'm trying to say here is, considering a mechanical system, considering a mechanical system where moment is accompanied by change in gravitational and change in gravitational and elastic potential energies, elastic potential energies, and where no work is done, no work is done due to non-potential forces, due to non-potential forces, or we can say that non-conservative forces. Okay, then what will happen? Then delta U dash, that is the virtual work done due to the non-conservative forces, is equal to 0. And what we get here is only, okay, since delta U dash is equal to delta V, therefore and this delta u dash is equal to 0. Therefore, we say that delta v is equal to 0. Okay, so we'll write this statement again. Delta v is equal to 0 when there is only the conservative forces, which are the active forces, and only the conservative forces are responsible for the virtual work. Okay, so let's interpret this statement. If a system is in equilibrium, and if the forces that do work if the forces that do work on the system as a result of a virtual translation or rotation, virtual translation or rotation, virtual translation or rotation are conservative. Okay, if a system is in equilibrium and if the forces that do the work on the system as a result of virtual translation or rotation are conservative, then the total change in the potential energy is 0. Then the change in total potential energy is 0. Total potential energy means the summation of the gravitational and the elastic potential energy. Okay, so we have a statement here. Okay, so this statement is written in the Merriam-Craig. For a mechanical system with elastic and for a mechanical system with elastic members and the members which undergo change in position, we may restate the principle of virtual work. The virtual work done by all the external active forces other than the gravitational and the spring forces, accounted for in change in potential energy terms on a mechanical system in equilibrium equals the corresponding change in the total elastic and gravitational potential energy of the system for any and all virtual displacements consistent with the constraints. Okay. Okay, now reading this statement again, the virtual work done by all the external active forces other than the spring and gravitational forces, okay, which are the conservative forces on a mechanical system in equilibrium equals the corresponding change in the total elastic and gravitational potential energy of the system. So what is this statement? This statement is actually this mathematical statement which you have already written here, that is delta U is equal to, this statement actually says that delta U is equal to, or rather delta U dash, that is the work done by all the non-potential forces. Okay, you can see that the work done by all the active forces excluding the gravitational and the spring forces is equal to the change in the potential energy. And further, and if delta U dash is equal to 0, that is the non-potential forces or the non-conservative forces are not contributing to the virtual work, then we can write that delta V is equal to 0. That is the change in potential energy is equal to 0. Okay. Thus, further we conclude that for a system of for a system of 1 degree of freedom, the potential energy can be represented as a function of a single coordinate theta. Okay, for a system of 1 degree of freedom, the potential energy can be represented as a function of a single coordinate theta. Okay, then the equation delta V is equal to 0 can be written as, okay, this equation can be written as, if it is a function of only one independent coordinate, that is, we can represent delta V is equal to dV by d theta, dV by d theta del theta. This has to be 0. Now delta theta can't be 0 because we are giving a virtual displacement. Therefore, we can conclude that dV by d theta is 0. So again, we can see that if it is a single degree of freedom system, just like in the previous virtual work topic, all these displacements were represented in terms of theta. Okay, that is, we might have various coordinates, xa, xb, ya, yb, xg, yg, but and delta theta, but all these were represented in terms of the single independent coordinate, that is theta. Therefore, again, if a system has 1 degree of freedom, then the potential energy can be represented as a function of single coordinate theta. Okay, sometimes in the books, this coordinate theta is a coordinate. Sometimes in the books have also shown q as the coordinate. Okay, if you refer the RC Hibbeler, in place of theta, the book has written as q. Okay, in the Merriam-Craig, it is represented in terms of x. Okay, but we can say that there is only one variable theta. Either you can say, okay, you can denote this variable or this, we can denote this coordinate or this variable by theta, q, or x, whatever we like. Okay, different texts have represented it in different ways. Okay, but I usually represent it by theta because in almost all questions we give we if you recall the previous virtual work questions, there the displacements were at last represented in terms of the delta theta terms. Okay, that's why I prefer to write it in terms of the theta. Okay, but you can see q and x in other texts as well. Okay, so this is what we have derived for the equilibrium. Okay, this is the condition which we have derived for the equilibrium. So to summarize this, we can write here is, what does this state? That in terms of the potential, in terms of the potential energy, in terms of the potential energy, the virtual work states the virtual work states or rather the virtual work principle states that that if a system is in equilibrium, the derivative of the total potential energy is 0. The derivative of total potential energy is 0. Okay, so this is the statement of the virtual work principle. for a system where the active forces are the conservative forces. So this is the condition of equilibrium in terms of the potential energy. Okay, so this was the heading potential energy as a criteria for the equilibrium, and at last we have arrived at the result that dv by d theta. Okay, d theta is an coordinate. Okay, it is an coordinate. It can be a linear displacement, it can be an angular displacement. Okay, it can will be seen in the questions what is this theta. Okay, either it can be a linear displacement or it can be an angular rotation delta theta. Okay, so this derivative should be zero. Okay, the derivative of the potential energy with respect to this coordinate should be zero for equilibrium. Okay, so in the next lecture we are going to discuss the stability of equilibrium, and we will conclude our syllabus with a few 3 or 4 questions using this principle. Okay, using the potential energy criteria for the equilibrium. Okay, thank you.